Hello students, welcome back to Chemical Kinetics. We are studying zero order reactions. Last time we did differential rate equation of zero order reactions. This time we will derive integrated rate law. Once we have done that, we will also see some alternate forms of the integrated rate equation. So let's get started. First of all, I want you to remember the differential rate equation for zero order reactions. This is what we studied in the previous module, that is minus dCr upon dt is equal to K, because Cr is raised to 0. Now here, the differential form of this rate law can be transformed to the integrated form by simple calculus, and that integrated form is nothing but the integrated rate expression for zero order reactions. So let's get started. Before we integrate this expression, I will need a differential term on both the sides of equal to, so I can rearrange this equation as minus dCr is equal to K into dt. Now here we have differential term on both the sides of equal to. So let us integrate this equation within suitable limits. When we do that, here we have our integral sign between the limits. We will discuss the limits. Let's complete the equation first. So it will become integral of minus dCr is equal to integral of k dt between these limits. Now take a look at the lower limit. You can say that when time is 0, the reaction has not even started. The concentration is C0. And when time is T, the concentration at that point of time is Ct. So here we have our limits. C0 is the initial concentration of the reactant when the reaction has not even started. Time is 0. And at time t, Ct is the concentration remaining. That's final concentration. So let's take these terms and continue our integration. This is the equation that we had. And in order to integrate, first let's take out the constant terms. So here we go. We've taken out the minus and k. This is what we are left with. We know that integral of dCr is nothing but Cr, and integral of dt is nothing but T. So let's carry out this integration. We will get minus Cr between the limits C0 to Ct is equal to K into T between the limits 0 to T. So after applying integration, let us now apply the limits, that is the upper limit minus lower limit. We will get minus of Ct minus C0 is equal to K into T minus 0. Open the bracket over there on the left hand side and you will get C0 minus Ct is equal to Kt. Now when you rearrange the equation, this is what you will get. K is equal to C0 minus Ct upon T. And this equation, my dear friends, is the integrated rate law expression for zero order reactions. Isn't it simple? Just take the differential rate equation and integrate it within the suitable limits. Now when we take this equation, the integrated rate equation for zero order reactions, we can also write some of its alternate form. For instance, if this is the reaction, reactants are giving products. The initial concentration is C0. Let's take it as A. And let us say X is the amount consumed in time T. That means when T was 0, the concentration was A, and at time T, X has reacted, it has gone away, which means that the remaining concentration, that is Ct, will be A minus X. The initial concentration minus the concentration which has reacted will give me the leftover concentration, the remaining concentration at time t. We all know this equation, K is equal to C naught minus Ct upon T. The integrated rate law equation for zero order reaction. Just substitute A and A minus X in this equation, and this is what we will get. We will get C naught is equal to A and Ct is equal to A minus X, and when we substitute it here, C naught minus Ct will become A minus X, the whole term in the bracket. When you open this bracket and when you substitute this C naught minus Ct in this integrated rate law equation, this is what you will get. K is equal to X by T, which means it is the amount which has divided by time. So that's your alternate form of the integrated rate law equation. That's all for this module. In the next module, we will understand the graphical representation of this equation. Till then, you take care.